Okay. So we are going to start with CST. So that is called as constant strain triangle. Okay. This is called a constant strain triangle. So basically it is a triangular element and it is a half element. So while meshing, you might mesh and you might get element of the such side. Okay. So this is in X and Y coordinate. Okay, this is in X and Y coordinate. Or global coordinate. Now this need to be transformed into local coordinate or intrinsic coordinate, whatever you want to say. Intrinsic or local coordinate. So we need to do the transformation so that my triangle would be like this. Here my coordinate system will be X and Y. After transforming into the intrinsic or local coordinate system, my coordinate system will be something like this. So this will be zeta equal to 1, zeta equal to 0, zeta, and this is neta equal to 1, and this will be neta equal to 0. So it is the half the element. So in this way, this transformation will takes place, and this eta and neta are the local coordinate. They belongs to the local coordinate basically. Okay, so X and Y is the global coordinate, and eta and neta belongs to the local coordinate. So now we need to find out the first thing is the shape function. So whenever we have the element, so we know we can use the formulation either isoparametric, superparametric or subparametric, whichever the formulation is there that we can use it, and for that we require basically the shape function that we should be aware of. So let's try to find out the shape function, and then we are going to use isoparametric formulation for the CST method. One thing you have to remember, it is a constant strain, and why that will be constant strain that we will see later on. But strain is constant, that also means we have a stress is also constant. So therefore stress and strain belongs to the element, and we should observe the elemental stresses and elemental strain. Okay, so I draw the figure. Okay, so this is my local coordinate system. This is eta equal to 1, this is eta equal to 0, this is, let us say, so I can call this as a 1, node 2 and node 3. So this will be neta equal to 1, and if I extend this, this will be neta equal to 0. So I am aware of So at node 1, okay, at node 1, I'll be having a N1. At node 2, I'll be having a N2. And node 3, I'll be having a N3. So 3 shape functions are there because 3 nodes are there. That is what is the but obvious. Okay. So N1 is 1. Okay, it will be 1 at 1 and it will be 0 at 2 and 3. So that this thing we are already aware of, and that many times we have done. So therefore I mark this as a 1. So this length is 1, N1 is 1 at 1 and everywhere it is 0. Okay, now it is a 2D element. So at 2 and 3 it is 0. So therefore I need to go and connect all these points. So I just draw this. Okay. So basically what I got this surface. Okay. And this surface is a representation of N1. So now we are dealing in 2D. So instead of curve now, we'll be getting a surface for a particular shape function. So this is how we get the N1 in case of CST. Okay, so just let me know by typing whether you have understood how the N1 look like. You can type Y if you have understood N1. बाकीचे काय करतात आहे? Okay, fine. So now here in case of 2D we have to use equation of line. Okay, so what to find N1? We have to use equation of line. Okay, or curve, whatever you want to say. If equation of line where N1 is 0. Okay, in 1D we were using the equation of point, but now to find N1 we have to use the equation of line where N1 is 0. So I could clearly see N1 is 0 at or on line 2, 3. Okay, so N1 is 0 on line 2, 3. So therefore to find out N1 I should use the equation of line 2, 3. Okay, so I could write N1 is equal to C into equation of line 2, 3. Now we know the equation of line 2, 3 is zeta equal to 0. So therefore I could write zeta only. Okay, zeta minus 0 equal to 0. So I could write zeta only. Okay, so I can call this as equation number 1. हे एवढं कळलं असेल तर 1 टाइप करा, नाहीतर प्रश्न विचारू शकता. Okay, so this is my N1. Okay, now I need to apply the boundary condition. So I know N1 is 1 where at zeta equal to 1. So therefore I'll put 1 C 1. So this gives me C equal to 1, and therefore I could write N1 as zeta. Okay, this is how I get the first shape function. Now I would like to go for the second shape function. So that is at the point 2. Okay. So again I need to draw the figure. So I can call this point as a 2. This will be 1. This will be 3. So this is 1. So this is zeta equal to 1. And this will be eta equal to 0. This is neta equal to 1. And this will be neta equal to 0. Okay. So I am looking for N2. So therefore N2 is 1 at node 2. Okay. And 0 at node 3 and node 1. And therefore I need to connect this point. So what I see, same surface what I was getting in N1. Okay, so whatever I getting in N1, same kind of stuff I am also getting in N2. Okay, the only difference is the orientation is different. So therefore, instead of going for full derivation, I could call N2 as neta. Okay, and I can label this as equation number 2. And if you have understood this 2, you can type 2, or else you have your questions. अरे 39 मुलं आहेत, काय करतात सगळे? बघा
नाव तिकडे का?
Okay. So now we are aware of, from the Lagrange's interpolation, sum of L, or I can say sum of all the summation function will be 1. This is already we have seen. So therefore, what we can write here in this case is N1 plus N2 plus N3 is equal to 1. So this is what earlier we have studied. Summation of all shape function is 1. So therefore, from this I could say N3 is equal to 1 minus N1 minus N3, sorry N2. Okay. And from this I could write 1 minus zeta minus neta. So this is my third shape function. In this way I could get it. So if you have understood this third equation, please type 3 or you may have your questions. Okay, fine. Now we are going to use isoparametric formulation. Okay. So this is my element. So this is 1 node, 2 node, 3 node. Remember, these are the local nodes, okay? Because we are working in a local coordinate system. So whatever the derivation we are doing it, that will be applicable to local coordinate system. Okay, and then we have to transfer into global coordinate. Finally, the stiffness matrix, global stiffness matrix, what we would like to have is in global coordinate. So according to that, 1, 2, 3 for an element will be a local, and then you could have Q5, Q6, or maybe larger number of displacement which forms a global coordinate. So that you'll understand slowly what I mean to say. Just like in truss, what we have 1 and 2 has to be local one. Okay. So therefore, this is my Q1, this is my Q2, this is my Q3, this is my Q4. So I am talking about this only. Okay, in global coordinate system, then according to node number, this will change. This is my Q5, this is my Q6. Okay, so these are the displacements of node 1, 2 and 3. Okay. Now, horizontal displacement is represented by U. Let us say horizontal displacement is represented by U. So since I am using isoparametric formulation, I write U equal to N1 Q1 plus N2 Q3 plus N3 Q5. So this is my horizontal displacement. I can label this as a equation A. Okay. So if you have understood this, type A, or you may have your questions. Okay. Now I am using V for vertical displacement, and that will be equal to N1 Q2 plus N1 N2 Q4 plus N3 Q6. So this is vertical displacement. I can label this as equation B. Okay, so now I know the value of N1, N2 and N3. So that is what I am going to replace. So U equal to eta Q1 plus neta Q3 plus 1 minus eta minus neta into Q5, and V is equal to eta Q2 plus neta Q4 plus 1 minus eta minus neta Q6. Okay, so by solving this again, I get U equal to Q1 minus Q5 eta plus Q3 minus Q5 neta plus Q5. So I can call this equation as pi. V equal to Q2 minus Q6 eta plus Q4 minus Q6 neta plus Q6. So this is how I can write the equation 5 and 6. Okay. Now the displacement I could write as, so I will label as a Q, u and v, that will be equal to okay. So from this I can write, okay, from A and B, N1 0, N2 0, N3 0, 1 0 1 0 1 0. Okay. So here I can write 0 N1 0 N2 0 N3. Okay, great. And I have all the vertical displacement Q1, Q2, Q3, Q4, Q5, Q6. Okay, so I can label this as equation number 7. So this is how the displacement will be related. Okay, and I can call this Q as N into Q, where N is this and Q is this. Okay, so now further, when we want to find out the stress, strain or stress, so we need to think about this Q. So we need to differentiate in x direction and we need to differentiate in y direction to get the strain in x and y direction, and later on multiplying with the material properties we could get the stress. Okay. Now since we are using isoparametric formulation, we also need to find out the relationship between shape function and the coordinate system. So we are using isoparametric formulation, therefore I write x equal to n1 x1 plus n2 x2 plus n3 x3. Okay. Now I can put n1 and n2 and n3 in this equation, and I can write x equal to x1 minus x3 eta plus x2 minus x3 eta plus x3. Yeah. Okay. So you can put these values of n1 and n2 and you can get this equation. So I can label this as a 8. So if you are able to understand this equation number 8, you can type 8 please. Okay. So now this equation 8 I can write as x equal to x13 eta plus x23 eta plus x3. Okay. So this is the basically equation 8. So what is x13? x13 is called as x1 minus x3. So x23 is what? So it is x2 minus x3. So you have to remember now from now onwards, if such term I like x13 and x23, so it means x2 minus x3, and the first term means x1 minus x3. So this is the short way we are going to use in finite element method. Okay, so whenever I write x13 or x23 or x56, so that means it is x5 minus x6 that you have to assume now. Okay, so that is the shortest way we write it. So from this I can also write y is equal to y13 eta plus y23 neta plus y3. I can call this equation as equation number 9. Okay, same way I could write this also. Okay, fine. So now we have 8, 9, and most importantly we have equation A and B. Okay, so A and B and 8 and 9, these are form the relationship. So because we have the displacement, we have the coordinate. So displacement is q, coordinate is x and y. So dq by dx gives you strain in x direction, dq by dy gives you strain in y direction. So now it's all about establishing the relationship, how the variation is occur and getting the differentiation. Okay. So before that, just we would like to do few things that we would like to implement how this shape function is calculated. Okay, there are few numericals which are expected, which is of what you say less time consuming. So that could be asked in the examination. So that we will try to do it. That how you can find out shape function, and with the help of shape function, how you could evaluate the displacement and how you could evaluate the various other properties. Okay, so we'll take one simple example. So there is one triangle. Okay, so this is the coordinate system, and we are talking about global coordinate system. So let us say this is 5, 5, and we can say this is 8, 8, and this I could say maybe 5, 8. Okay. So I could say this is 7, 10. Okay. So this way I could assume the coordinate of this. And there is a one point here. Okay. There is a one point here whose coordinate is, so I will assume 7 and 9. Okay. So I just ensure that this point lies within this triangle. I don't know, because I randomly assume the point, and I want to ensure that this point lies within this triangle. So I am assuming a very close point, 7 on the same line, and just one value below it. So naturally this is the 8, so it will lie within this triangle. So 7, 9 is the point. Now what is my target? I would like to find out the shape function at 7 and 9. So I can label this as a 1, 2 and 3, and I can label this as a point A. So what is my target? I want to find out shape function at A. So this is what is my target. Okay, so how I am going to do it? So let's try to solve this problem, because you know it varies in 2 dimensions within the element, and though it is a half element, we can still find out the shape function. So now we can write the first formulation, that is x is equal to x13 eta plus x23 neta plus x3. Okay, so my x here in this case is point A, that is 7. Okay, x1 minus x3, so this is 1 and this is 3. Okay, so x1 minus x3 is minus 6, and then I have x2 3, x2 minus x3, so this is 2. Okay, 8 minus 7 is 1, and value of x3 is 7, so I could write 7. Okay, now I can rearrange this. Minus 6 eta plus neta is equal to 0. So this is my equation. I could label this as equation I. Okay. Then from the second equation, I could write y is equal to y13 eta plus y23 neta plus y3. And from this y is now 9. So I write 9 here, y1 3. So y1 is 5, 5 minus 10 is minus 5, y2 3. Okay. तर चुकलं का? थांबा बघतो. x13 is minus 2. x13. So x1 is 5. Five minus 7 is minus 2. Sorry. It's not minus 6, it is minus 2. Okay. So I got minus 5. Now y2 3. So y2 is 8. Okay. And 3 is 10. So again I get minus 2. So minus 2 neta and y3 is 10. Now I can label this as equation 2. Okay. No, not 2. I need to simplify it first. So I can write from this minus 5 eta minus 2 neta is equal to minus 1. This is what I can write. Okay. So if these equations are clear, solve this and let me know eta and eta. Okay, so I have 1 by 9 and 2 by 9. Okay. So anybody could tell me in decimal place, please, in decimal. Okay, so I have 0.11 and I have 0.22. Great. Now you have to remember one important thing. I keep on calling half the element. Okay. You have to remember this is eta equal to 1 and this is eta equal to 0. So variation of eta is from 0 to 1. Okay, and that is why I am calling this as a half the element. Up till now what we have studied, it varies from -1 to 1. Okay, and this is full element. Since here in this case triangle is a half element, our variation is 0 to 1. Okay, so we have to ensure that these values, whatever we are trying to find out, should lie within 0 to 1. If you are not getting that thing, okay, if you are getting something else, okay, sometimes you make a mistake because those values might be in -1 to 1. This is what is your assumption, but you tend to forget that it is half the element. So this range is not valid for triangle. Okay, the range which is valid for triangle is 0 to 1. So your values of zeta and eta should fall between 0 to 1. If that is not falling, that means you have made somewhere else mistake and you need to do the correction. So that is one of the important thing. So if this concept you have understood, you have to type U, please. So basically triangle is a half the element, and here in this case the variation of zeta is between 0 to 1 and full element variation is -1 to 1, and we have to ensure our values of zeta and eta lies within 0 to 1. If in case of calculation, if your values sometimes fall between -1 to 1 because of certain errors in the calculation, and student accept those values assuming that -1 to 1 is the correct range, but this range is applicable for full element, which is not applicable for triangular element. The range which is applicable for triangular element is 0 to 1. So if your zeta and eta you are not getting into 0 to 1, that means we have made the mistake. This is the way to find out the mistake. Sometimes you make a mistake and your value lies is this within this zone and you accept it, but that time you are not able to recall that it is a half the element and their value should lie within the 0 to 1 and not -1 to 1. This is how we have to remember the values of zeta and eta. So most of you are likely going to make this mistake. They are going to accept the values of -1 to 1 because of the errors in the calculation. Okay, so you need to avoid this. You have to if you are getting that value, okay, it's wrong. My value should be between 0 to 1 and not between -1 to 1. I hope now if you have understood, you can type U. Triangle is a half the element. It does not cover the full dimension. Okay, this is the full element, but it consider X and it considers the Y, where in this case it does not take into the full dimension. So therefore it is a half the element. Okay, so all the quadrilateral elements are full elements and all the triangular elements are half element. Now we would like to add one more thing into the same problem. Let's say temperature at this location is T1, temperature at this location is T3, and temperature at this location is T2. Okay, and T1 is 100 degrees Celsius, T2 is 0 degrees Celsius, and T3 is 200 degrees Celsius. So these are the temperature ranges given. Now you have been asked what is the temperature at A. Okay, so we are going to use again the isoparametric formulation, T1 is equal, sorry, not T1, T is equal to T1N1 plus T2N2 plus T3N3. So I can call this as a TA is equal to T1 is 100, okay. My N1 is equal to this one, 0.11 plus T2, my N2 is 0.22 plus T3, and my N3 is and my N3 is 1 minus 0.11 minus 0.22. So 1 minus zeta minus neta. So that is what is the stuff. And from this you can get now TA. Okay. So just let me know the values of TA, please. So TA belongs to temperature at A. Okay. So we have the values of 144.5 degrees Celsius. Okay, so this is the value what we are getting it. So similarly, one could provide the displacement like Q1, Q2 and Q3 horizontal displacement at node 1 and node 2 and node 3 respectively, and also vertical displacement like Q2, Q4 and Q6 at node 1, 2, 3 respectively, and they may ask you what is horizontal and vertical displacement at particular point A. So in that case you have to use this equation A and B. So Q1, Q3 and Q5 will be given, Q2 and Q4, Q6 will be given, and you may have asked what is the displacement at this particular point, which is represented by basically U and V. So you can use equation A and B in that case to find the displacement. Okay. So just to understand more, I just have taken the example of temperature. It is also likely possible you could write sigma is equal to sigma 1 N1 plus sigma 2 N2 plus sigma 3 N3. Okay. So these are the possible cases what you could evaluate it, but this is a very rare case. They will ask you the temperature and the displacement it's a most common practice. Okay, so you do not consider these at all. So temperature is there, displacement is there, so that is possible. Okay, fine, thank you. So today we are going to stop here. Later on we will continue with the more detailed analysis of CST. So thank you. You can start leaving. Yes?
Sir, is there any other way to calculate the temperature, as we do not know how much accurate it is?
No, this is based on our assumption. We have assumed whatever the polynomial here in this case, that on that assumption we are trying to find out. Okay, it is based on Lagrange's polynomial. So we are assuming a linear polynomial. On that we are trying to find out. Okay, to improve the accuracy we can go for quadratic, cubic, and so on. Okay, so you can start leaving. I have another lecture now.